Matthias's presentation, just with a bit more of a focus on electron diffraction and what's new and what has been introduced over the last year in our electron diffractometers. It's also maybe a bit of a kick-off for the lab tours. We'll also see the electron diffractometers there, and I want to give you a bit of an insight what we have now and what we can discuss about further. And what I would like to focus on, we've heard already a nice bit of, quite a bit of dynamical refinement, absolute structures, sample preparation. But one thing that Claire already pointed out a bit, and also Jerry, is that, of course, electron diffraction is also sitting somewhere in between single crystal and powder, in the sense that its true superpower is that you do not only necessarily analyze from one of those crystals, but if you have a TEM grid in your diffractometer, you have tens of thousands of millions of a lot of crystals, right? And they differ in quite a lot of aspects. Like, first of all, these can of course be mixtures, has been mentioned already. Mixtures, contaminants, different polymorphs. And each of those crystals can have, will have limited completeness if you have a low symmetry. And so the data you will get from one of them is not necessarily the most useful and not the most complete. So the power of ED is really unleashed only if you do have some automation to do multi-crystal workflows, to do automation and also data management and bulk data analysis. And I want to start with the automation portion of this. So you may know that the Synergy-ED allows you to build a queue of measurements that then are run in an unattended way for different tasks. So just for screening, so if you have a lot of amorphous, decomposed, ugly goo, and then every once in a while a beautiful little crystal, you may not necessarily want to waste your entire lunch break on searching for it if the machine can also do it without you. One thing that's maybe even more relevant is mapping of different polymorphs which you may have on your grid, or different substances altogether. So automatically just screening them, if only for unit cells, but maybe even for the structures. But we'll talk about cells mostly. And then, of course, if you have pre-screened crystals that you know diffract well, just collecting from them. Collecting from 10 or 20 for merging data, get a higher quality data set. One essential feature that we introduced, it was hidden in CAP44 already, tucked away in a corner. I think nobody found it, and it was good that way because it wasn't working well. It's automatic centering of crystal grains. So this is really an essential feature for all of this, because if you enqueue crystals on a measurement list, you don't want to center each one separately. So as you may know, in an electron diffractometer, the crystal centering works just as in an X-ray diffractometer. You rotate the crystal and keep it on axis. And very same is done here. You see that red cross following the crystal while the gonio is being rotated. And then once it's rotated to a certain angle, so here's 50 degrees, you can even go higher, the algorithm will just check, okay, this is where the crystal has gone to, and bring it back to the center. Developing this algorithm has taken quite some time because it was actually much less easy than we thought. In cryo-EM, this is something that everybody does, and it's fairly standard, but in cryo-EM, your samples are perfectly planar. They're absolutely flat. And if you rotate a 2D object, you roughly know what it's doing if you're at a different angle. Here you have a 3D grid with like stuff that's overlapping and big rocks next to each other. That made this much more complicated than we anticipated. So very happy that we have this now figured out. So kudos to Matthias and his team. Who've done a great job here. Now about this automatic screening. This is just what I want to show you how this would work, because I think it's maybe the most powerful application of automation we have right now. So this is just the way you set up a queued measurement in CrysAlisᴾṕ. You have the measurement setup window, just as for a single measurement, and then instead of just collecting the measurement the crystal, including the collection parameters, will store it in this window along with reference image of the grain you want to look at, so it can find. So the machine can find it later on. You can drive of course, the go in your head or the stage back to that position, but usually there's some error associated with that, so you'll have to find it back anyway. Then you do that. For some reason, you still have to miraculously click Auto Center every time. This is a feature request. If you get used to it, it becomes second nature. But so you just fill up this queue, and this is in fact a grid which I, on purpose, just prepared with a lot of different substances, a whole mix of different stuff. Okay, well, obviously running this at an increased speed now.
It reminds me of watching Hongi center crystals in Sweden.
Yeah, Hongi is efficient. Kind of scary at times. Did you use the trackball? Yes, yes. So for this, you're actually faster if you use a trackball, to be honest, than if you just click on the grains. So if you're in front of the machine, then just use a trackball. For these automated queues, you don't have to worry about things like backlash compensation anymore, like you used to in CAP44 in ancient days, where you always needed to, I don't know, approach this grain from the same direction when you wanted to enqueue this. Not anymore. In CAP44, just, you know, as long as it's on the crystal and you see it properly, all good. No setting the height, no relaxing the stage. It'll all take.
Is it good with other grid types, or is it still used continuously?
Let's say we haven't tested this enough. I know that the stuff that you're using, these funky, holy things from Agar Scientific, give it the most trouble because they have features that are in the similar size range as the crystals. We haven't tested those too much yet. Anecdotally, lacy carbon works okay. Generally, it gets trickier and trickier the smaller and more translucent your crystals are, which is sort of obvious. There are a lot of parameters in the auto-centering that can be tweaked to your liking, using at the moment some parameters that are a bit arcane, but we're working towards making this into, let's say, a preset system that gives you a bit more guidance on how to set them. So this is not the actual data collection. I kept the slightly increased speed of the video. So one thing that we're now working on for CAP45 is to actually get it not quite that quick. So its speed is 16 times now, but make it much faster. So our aim is to go to roughly 1 minute per grain. I think that's realistic. At the moment, it takes still around 3 minutes, most of which I think we can just shave off if we make the whole process a bit more efficient. But what you see here is that the machine just very efficiently finds the grain, centers the grain. Whenever some automation is running, it turns red.
And red means that you have full beam, yes?
No.
Or you measure?
You're on visual mode.
Yes, yeah. This is just your visual mode, and you center the grain, and then you switch to the measurement, and then
Visual mode or usual mode? Yes.
yeah, it's a screening mode, or the screening mode, which we call visual mode, or the measurement.
Robert, I have a question. So the beam conditions and the time of the measurement, this is fixed, or you can?
No. You can set this for each grain. You can even set it for each grain separately, though. For this kind of screening task, you would usually think of reasonable parameters. My personal favorite for this kind of task is rotating -20 to 20, because that usually is easily enough to give you a reliable unit cell, and not wasting too much dose on them, because you may want to collect again from the same one later on if you figure out that you have a particularly nice one, or let's say an odd one out. If you're looking for that last one among the flock,
yeah,
then you want to save some dose for the actual data collection, right?
Okay.
Okay, I can look at this forever, but we got to move on. Yeah.
Can we set a condition? Suppose we keep getting the same unit cell, so we don't need to collect data. We can keep finding new feeds.
Sorry, you mean automatically?
we get plenty of sample on the grid. But suppose 10 of them has exactly the same unit cell, maybe we don't need to collect data. So we keep focusing on new unit cells. Is that possible? So suppose it's this unit cell, we stop.
You stop the measurement and then, well, it would technically be possible. We think of something like that for ice, just like an ice immediately auto stop routine. But this was already, like, let's say, the minimum degree of rotation you need to reliably determine the cell. Because due to this flat Ewald sphere, which Horst has nicely shown, you only get 2D information out of a single pattern. So unlike with X-rays, where you see a single still pattern and get a good idea about three-dimensional unit cells, it's not possible with electrons. Why is it
save lots of time at the end. And it's better to have more data. I tried I know what you asked. I tried it. Does it save time?
Stopping an ED data collection is longer than letting it just finish last time. And the user's like, why are you still doing this? I'm like, you'll see why, just let it happen. You know.
So we then have nice data management tool, the ED results viewer, and I actually wanted to show just a very quick live demo on this. We don't have too much time, but let me just, I'll be really quick, I promise. So, because one thing that we now also have, which especially for this type of queues, is quite handy. So after the queue, or just with whatever you have on your hard drive, you get now this viewer, which sums up all the measurements you've taken, has a lot of customizations, it has very useful filtering, because otherwise you have thousands of data sets in here, can filter by a lot of criteria, it's quite nice. And one feature you can also have is now this is the result, in fact, from exactly that measurement I've just shown you. And now if you want to see what unit cells there were in this sample, you don't need to anymore just to look through them and sort them manually, but in fact we interface now to a tool that does this for you, which should be starting right now. Here it is, which just by means of hierarchical cluster analysis just sorts those data sets into bins with identical unit cells. I don't want to go into too much detail. You can set up certain parameters of how this clustering is done, set a threshold, how close cells have to be considered the same cell. But here you see now, for example, if I set a threshold here, I could reasonably identify that we have 1, 2, 3, 4, 5 different compounds here. Here I have the list of the averaged unit cells of each of those clusters, including the standard deviations, which just tell me, like, is it reasonable that those are the same? I can look at the histograms of the cell parameters. There are a bit too many components right now here to really make sense of this, but here you can confirm once more that these are actually distinct. And what I don't have the time now to show you is that also in this interface you can right away merge data sets, such that for each of these nodes here, which always have is a certain combination of data, you get a merged compound data set and straight away run this through scaling and processing, and then look at the resulting, let's say, shell-dependent figures of merit, just to check which gives you actually the best data quality. Because it might not be that, let's say, this node here, which merges all the green crystals, gives you necessarily the best data set in the end. Maybe this one, these two, which are a bit more different than the others, will just not contribute in a meaningful way, and it's better just to pick only those.
I have a question related to this. So it does it just directly, it doesn't, for example, recognize if it is a very bad crystal after or getting a very bad merged data set to go back and revise this?
No, it's at the moment still in a very, very simple stage. It's at the moment just clustering it based on the unit cell, which is also not optimal. Of course, in principle, you would want to cluster on intensity-based metrics.
Yeah.
The dials people are investigating this a lot now. It's trickier than it seems.
Yeah,
The intensity-based merging, you could just go for cross-correlation coefficients, but you run into other nasty things, then I have some prototype codes which do this with data from CAP, which first do a scaling all of them together, and then let's say look at correlation coefficients of each individual one against this and with respect to each other, and then I could imagine a good way of doing it might be some global optimization along the lines of a genetic algorithm. Okay. But maybe, I mean, at this point we're halfway to AI. But maybe more old-school global optimization, like a genetic algorithm that picks random combinations and then kicks out outliers iteratively. So if anyone has a student who would enjoy working on this, please give us a call and we'll be happy to provide any sort of support.
It's still a check in the result viewer, the very bad data set, by filtering.
Yeah, of course, you can still do that. I mean, if there are obvious outliers like see, I can hear in the filters.
No indexing or no solution or stuff like that.
Yeah, of course. No, that anyway. If there's no solution, it will just ignore it. And for example, if the unit cell, I can ask it to only include grains which are indexed to more than 30%, and it'll kick them out. And then only supply to the clustering tool what you have in that list. Okay. So just for a simple sanity check, those filters in this lower part. Also, you can exclude cells, like you can put this exclusion parameters for ice. Okay. Just as a random example, right? Okay. I think I'm almost out of time already.
You can have 5 more minutes if you want to show.
5 more minutes? Okay. Yeah. I'll maybe this time I'll stop using the timings. Because I want to show you at least one more nice thing that is only semi-related to this. Just here, this is the interface you get once you run the merging. So you have like different, like for each of those nodes, you get a line here. You can then look at the resolution-dependent metrics and compare them by just selecting several of them, then have resolution-dependent plots of figures of merit to select here. And these nice radar plots, which give you, let's say, an overall comparison in the overall and highest shell metric. This is, of course, all stolen from what people did in CCP4, I think. It's pretty much the user interface of Aimless, which I copied, but because I think it's good. So.
Can I ask you something else, or it's not the moment? If you have, for example, one case where it's always indexing in C, but you know it's P-1 or it's P1 and it makes always systematically a mistake by indexing. Is it a way to cover this before doing all the work?
Unfortunately not. This is a notoriously weak spot, is that we have no efficient means, even in the results viewer, to do any sort of bulk processing or bulk changing to data sets. This is a very high up on the let's say backlog to-do list for CAP.
Okay.
But as CAP follows a paradigm of more like looking into single crystals and not so much into bulk, it's not so easy to implement. So, but we are fully aware that this at the moment is a stupid situation for electron diffraction. That often you have 5 data sets. You know that all 5 are wrong in a consistent way, and you still have to click through each one, make 40 clicks to get them all on the same. It's stupid. I know.
There is like a workaround I can show you, but it's not really.
Yeah, no, usually you can ask Jakub and he will have a workaround of like 20 arcane commands in CAP, which you just have to run on each single one, and which...
It's not what we would like to leave it as a final solution.
Yeah, that's not how we picture our software working, you know. So please, I hope that CAP45 will be much more benign about these things.
This would be nice.
Yeah, no, fully appreciate it. I couldn't agree anymore. This is really one of my pet peeves for 2 years now.
Okay.
I get some maybe stupid idea. Can we force the software always solve the structure in P1, and after that we use plugin to verify the true space group? Basically doing the shellXT approach on the full pipeline. I heard that exact suggestion in Stockholm on the ED meeting last week. Might not.
it's also a bit in this direction of why not just throw AI at the problem.
I want a job is why. I want a job is why.
I have user-inspired question. You inspired me to when you asked why did I stop the stuff that I don't measure. I think that could be useful if you have in your cluster analysis accidentally measure contamination in the unit cell. You could probably get better sigmas from the cell you know, and then we apply that on the unknown unit cells. Maybe think about this, like using like reference, internal reference to make the unit cell slightly better. Because you're measuring the like ice or something like that,
yeah.
just lock down the unit cell.
We have there is also something we are considering. Let's say if you have for full data collection, there's like an overall net deviation in the unit cell from what you have locally as a reference, or even what you have in the CSV. That this suggests you that probably your calibration is just off. It's also quite straightforward. So yes, it's a good point. Just one final thing, because that's new in CAP44 and that's cool, is we are phasing in now more and more multimodal measurements. So because as everybody correctly says, it's a complementary technique to everything. So we should also be able to correlatively manage all the data together. So what we have now in CAP already is the capability to ask for post measurements that you can do on single measurements, but also in queues. One would be that it automatically switches to a higher magnification mode, and in contrast to what Jerry just says, there is a number of higher magnification modes which we make accessible from CAP, which do not screw up your alignments. We tested this very thoroughly. So it allows you to take post measurements of a grain. So this is 500 nanometer. This is like a typical ED grain, and then you get much better idea how these things look like. And as Claire already pointed out, even the tiniest of grains, you wouldn't think how ugly they are, and how twinned, and how contaminated, and intergrown, and everything. The second thing, which is something that you may be used to from your X-ray machines, is that we can also take stuff like tomography data sets, where you could even now, if you're keen to fit crystal facets on it, even though for these super small crystals, I'm not sure how much that would actually gain you. And then there's Dan's new toy, which we'll also get next week here, and hopefully on many more installations soon, is EDS, which is also in this post-measurement framework, because as the two others, this is a high-dose technique which will just fry your crystal. Afterwards, it will not give you high-resolution diffraction data anymore. Okay, I'll skip the video to show this. Just here, because it's so nice. This is from one grid. This is actually data I took just yesterday. So where here you have, let's say, 5 different grains. And for each of them, I have now a data set. This is how the grain looks like at high magnification. This is how the grain looks like as a tomographic series from all sides. And this is how the reciprocal space looks like. And maybe we can have some AI which will correlate this and give us even some insight into how morphology correlates to what's actually what that rock actually is. The more information we throw into this. Now we also think about adding powder into this to give a bit more of a prior and so on. So just becoming more multimodal. Same for like the EDS. It's also fairly straightforward. So this is the EDS post measurement. It's actually the only video I have so far because Dan allowed me to just take it on the on his machine in Southampton. It's probably the first case where they got it before us. So there's just ways in CAP to set up the electron optics of the whole instrument such that it gets optimized not for diffraction but for EDS, which is exactly at the opposite end of what you want an electron beam to do. For EDS you want to fry your crystal as hard as you can, which is exactly not what you should do for electron diffraction. And then while it's being fried, and you still see that there are some last creams of diffraction coming out of it, you see how the X-ray spectrum is accumulating. And just a very, very final outlook. This is more for CAP45 than for 44, but let's see is there's also now a well-hidden feature to make the screening even faster. So instead of just moving on each grain and adding it to a measurement queue, just click them and they get added down there.
And then ideally at the end you also will see that every grain, let's say color, which phase it corresponds.
Yes,
Like label. Label.
That would be absolutely excellent, and that would probably need a few changes to how they are displayed, but this is also something like feeding back.
Feeding back, yes.
So the way I would love to see this is that each grain you can actually click and you have a little pop-up which tells you afterwards. So
what was the unit cell?
This is the unit cell. This is how well it's diffracted by some figure of merit. And then maybe after the fact, even, and this is how the spectrum looks like, and the elements that were in there, and here's some SEM image that you took before. Something like that. So, of course, this is a long way to go, but this is, let's say, how we imagine how this would progress.
Check it button.
Check it. Oh yeah, then also send to ChatGPT to write the paper and publish. And then the very final stage I just want to show you this as well. The final stage of automation, then, this is even more hidden away, is that we also have a means to just not even do this, but just find everything that's in there automatically and put green crosses on it, and then maybe add the ones that it missed. But this is, we will not release this before we're really certain that this works well enough.
This is going to be 45, you said?
This is rather going to be 45. We're starting testing, but of course there's a lot of corner cases to be tested here to make this reliable. And there's of course a danger of, a question in this regard is, and I think this has already been raised by Jerry, if you have a mixture, both you and the machine would not necessarily pick something that is representative, because maybe you have a large volume component that makes big crystals that you cannot go through, and then you'd be biased exactly other way around as an SEM. So I don't know if the machine will be more biased or you, or there are many things to consider here.
Be very consistent in its decision making.
Yeah, I think the first step would be to make the auto algorithm quite consistent with what a human operator would do. And in fact, this is a case where really AI is probably the proper solution for image recognition, or just for, let's say, normal frameworks which are standard by now in fields like CrysAlisᴾṕ, like YOLO, or things like that.
So you need to go first step of proper sample grid handling. You need the proper density loading on the grid, proper grid, and so on.
Of course, but that's what Jessica.
Yeah.
That's what Jessica is doing for us. And you guys. Okay, sorry, it took so long.
That's okay. I think it's all useful, and we were about 10 minutes behind anyway, so you didn't have to take any more.
And I'll be here today, tonight, tomorrow. Just keep nagging. Appreciate it.
Yeah. So now we'll go for coffee upstairs.